Good morning, dear colleagues. Huge thanks for committee members to serve as a committee members today. And today I will present you my PhD proposal defense for the topic of efficient optimization and compression methods for large language models. And here's my plan for today. I will start with how large language models work and what are its main problems. Then, as we understand the problems of LLMs, we can start thinking about how to make it more efficient and faster. And we will do it by the method that I developed while my MS here, which is called Thanos. Then I will tell you about Supra super tuning. When you have efficient model, it works fast, but then you want the model to be very good at specific stuff, and you want to, efficiently train it for it. And finally, I will tell you what you're gonna do if the model is so large that it cannot be fitted on a single device, but you still want to train it. In essence, the large language model is just the mapping of the input sequence, input tokens, into the probability distribution of the next token. Every token on the input can be represented as a high-dimensional embedding vector. And as you generated the next token in the sequence, which in this case is ones, you can continue to generate a larger corpus of text by using this autoregressive manner. You just concatenate the answer from the previous step into the input on the next one. Of course, the most interesting part here is large language model. Let's dive in. It consists of similar blocks of nonlinear transformation that operates on the input embedding X. And let's consider one of this block. So we have input matrix X. As I mentioned, it's just the matrix of embedding vector that we have on the input. So every row of X is just high-dimensional embedding for a particular token. Then we compute what is called queries and keys, which helps us to understand the correlation between different tokens in the following way. For every token, for example, for the token right, we want to know what information is important for this token. And then to understand what information is important, we compute the keys and queries. And keys answers the question how to attend this particular token. Queries answers the question what is important for this token. And in order to understand the correlation, we just compute the dot product between queries and keys. And this is called a QK score. After we have it, we compute the value matrix, which answers the question what information is important for every token. Then we can combine, after we have the QK score, which answers the question what information is important for every token. We combine this information from the matrix V, and after a bunch of other linear transformations like down and up projections and normalization, we have the output. What is important here is that all these parameters are just linear layers, matrices, and if we want to make LLM faster and better, we want to just optimize these linear matrices. After we have the output of the first block, we give it as an input to the next one, and so on and so forth, until the very end. And that's how it basically works. And the problem is that it's very large. As you might know, it can be from billions to up to 5 trillion parameters for ChatGPT. So we want to make it faster somehow. And the first work that I'm going to mention is pruning by Thanos. So imagine that you have a matrix W. What you can do here, you can just select smallest half of the parameters and remove them. And that's called a magnitude pruning, but it doesn't work too well. The problem of this approach is that we only consider the W itself, but as I mentioned before, the output of linear layer is the multiplication of W and X, where X is the input. And the loss that we want to consider is the following, where W hat is the linear layer after pruning and W is the linear layer before pruning. So this loss actually tries to minimize it tries to make the output of the linear layer to be as close as possible to the output of the linear layer before pruning. And Fabinius norm here is just the sum of all entries of the matrix squared. And we can rewrite this loss in the following way, where delta is just the difference of weights before and after pruning. So that's the loss we want to minimize. And what is good is that we can rewrite this as in this row-wise manner, which actually makes the problem much simpler, because now the problem for every row is independent. If you want to remove parameters from a single row, you just have to minimize this loss for the loss for the specific row. And if you want to remove just a single weight from a row without touching other weights, here is the optimal loss that you will have, and it's called the Wanda score. And what Wanda does, it actually removes half of the parameters by using this score, and it works much, much better than just magnitude pruning. But as I mentioned before, the Wanda score is optimal only when you remove a single parameter. And the next problem with this is that you have these green parameters that are not removed, but you want to try to compensate for the error that you caused by pruning parameters, by pruning red parameters. And that's exactly what was done in sparse GPT. They tried to adjust non-pruned parameters. So you have the same loss. You have this constraint that this one weight that you want to remove should be removed. And you can tune all other weights. And here is the rule that they obtained. That's the rule of how you should update all parameters in a row. H here is XX transposed. It's the Hessian of L2 loss. And if you want to remove one single parameter in a row, you just apply this rule for all parameters. And the question that I asked while working on Thanos is that what if we remove few parameters at the same time, not just a single one? The next question is that in sparse GPT, you just fix the mask before pruning. You decide on one parameter should be removed, and then you fix it, and then you prune step by step. Which is not optimal, of course, because parameters can change, and this change of parameters while you prune the model can be important, so the change will cause the change in ordering of importance. And we answered on the first question by solving the same L2 loss, but now we have S constraints, where Q1, Q2, and Qs are weights for indices of weights for removal. And we got the following rule that basically answers the question how you're going to update all parameters, all non-pruned parameters, in order to optimally remove selected parameters. This is good because this is a closed form solution formula, and it's very simple and computationally efficient. It consists of the matrix R, which is just the combination of rows from the Hessian, the matrix R hat, which is combination of columns from R, and U is just the weights for removal. The complicated part here is the inverse of this Hessian, but if you limit the number of parameters you remove at a time, it's very efficient. In this particular example, we divide the block into 4 parameters at a time, and we proceed the whole matrix row by row, and we update all parameters in a block-wise manner. As we finished with one block, we just proceed with the other one, and so on and so forth. That was the answer for the first question. So yes, if you want to remove few parameters at the same time, you can do it more in an optimal way by using our closed form formula. But also the answer for the next question is that we can basically make the mask dynamic. And what we do is exactly the following. We compute the Wanda score in the very beginning of pruning, and then we only consider a small portion of weights that are important for us. We update this, we prune this, and only then we move to the next block. It's like a residual portion of the matrix W, and then we compute the Wanda score again from the very beginning. So this is computed on already changed parameters, and then we consume only a small portion of this Wanda score, which is essentially the block that we're gonna prune right now, and we do it in this, recursive manner up until the point when we prune just all parameters. So basically, Thanos contains both dynamic mask and optimal update rule. On the optimization, on the computational efficiency side, we were able to make it even faster and more efficient than sparse GPT for smaller models, but of course Wanda is faster than both of these sparse GPT and Thanos methods. On the result side, we see that comparison with the best baseline that we had, Wanda and sparse GPT, Thanos is better in almost all cases in all structured and unstructured pruning and for all patterns and model sizes. So that additional complexity actually worth the effort. The next work, now we have the model that is efficient and can be, half of the parameters are already removed. It's good. But, the LLM can be very good at some generic stuff, but it can be bad for some specific stuff on some specific problem. In this case, people just consider, like, if you have M weights, M linear matrices in your LLM, and every matrix is a two-dimensional matrix. It has some shape. And then you want to minimize the following loss. Here, D is some data set with specific task. And W bar is this other weights, one-dimensional biases, which are less than 1% of parameters. So you want to minimize this loss for this specific task. And the problem is that it might be too expensive because of the fact that you use entire model. So you have to basically store the adapter for the full model in your memory. What people do instead, they define the following adapter, delta. For every matrix, you define delta matrix with basically the same shape. I'm sorry. And then you use this delta, you add it to the pre-trained frozen model. And one can say that, so you basically didn't save anything because you added this delta, which has the same shape as the initial model. Yes, but unless you add some constraints. For example, you can make delta to be rank R, which can be represented in the following way. Gamma here is the scaling factor, and LR are low rank factorization matrices. And this is basically one of the most famous way of fine-tuning your model, which is called LoRa. But you can use other type of constraints. For example, you can select only a small portion of trainable parameters. Zero loss here, zero norm here means the number of trainable non-zero entries, and you limit it to be a small portion of the total number of parameters. So basically, you select very small number of trainable parameters, and you allow only to train along these directions. This is called a sparse fine-tuning, and that's exactly the method that we contributed. The method that we contributed to. And the problem here is that how to select these good parameters for training. So green are trainable parameters. And you see when it's coming to, because the problem that we just solved in pruning seems to be very similar to the problem that we are solving now. Because there in pruning, we had to decide, we had the constraint that we have to remove half of the parameters. So we basically have to decide what parameters are important. Here, the problem is very similar because we need to decide what parameters are important for training. And these are kind of complementary problem. That's why basically our work is called From Activation-Aware Pruning to Sparse Fine-Tuning. And we notice this connection between these two problems. Although mathematically they are not the same, of course. You can use different methods for selecting these good parameters. For example, you can measure the magnitude of the gradient and train the most active parameters. Also, you can measure the magnitude of every parameter and select the smallest one, hoping that you will not hurt the performance of the base model. And what we suggest is to use the same Wanda metric that we used for pruning. And the intuition here is the following, is that, so if you have a metric that shows you how important parameter is when you remove it, basically that can give you a hint on what parameters should be trained if you want to train it for a specific task. Basically, you can do it in two ways. You can select top k parameters, which are the most important, or you can select bottom k parameters. Initially, I thought it would be great to train the most important parameters, but it turned out that bottom k selection gives the best result. So basically, you have to select parameters with the smallest underscore, and one of the reasons might be because you don't hurt the performance of the base model. So how to test this method? So we have the method of how to select trainable parameters, how to test is it good or not. And general way how we can do it is the following. We have six mathematical benchmarks. These are different math problems with like hundreds or even thousands of questions. We give it to LLM, for example, ChatGPT, and then we have the answer. For every benchmark, we have the score, the average score. And then we can find the average throughout all of these scores. For ChatGPT, the number will be very high, of course. These are not the real numbers, just for showing you the concept. But the problem is that ChatGPT is very expensive. Of course, it can solve these mathematical problems. They are very simple. But what if you want to, run your own tutor, which not be as expensive as ChatGPT? The answer is right here. You don't see it, but you have to zoom in order to see it. So that's basically Llama 3.2 1 billion, which is basically for free. You can run it on your mobile phone or on your laptop. And we did the same. We measured the average score for every single mathematical benchmark. And you can see now that the average is not that high. So that's basically the area where we can try to apply our new method. So we have a base model, Llama 1B. Then we have a mathematical data set, 17K of answers and solution for them. Every such example from the training set contains the question itself. Then we have a reasoning how to solve this problem. And we have the answer that we expect from the model. After 1 or 3 epochs of generation, we have Llama on steroids that we can now test. And here is the training loss. We can see it's becoming smaller and smaller. For our Supra, the line is the best. And here is the validation loss. It's also becoming smaller and smaller. And here are the results. You can see that our methods, on the left you see all of the baselines. And here is the method that Supra, that we developed with this pruning selection of trainable weights. And it's right behind the full fine-tuning, where you allow all parameters to change. You can see like a similar picture for 8B models. So our method is still the best here. So now you have a very good model that is very efficient, and you trained it for mathematics. But now you probably want to move back from this very small model and think about ChatGPT, or maybe dream about it. And now you have the problem that you want to train it, but you don't have, so it's so large that it cannot be fitted on one single device. And what people do regularly in this case. So imagine we have LLM, and now we have few devices, few GPUs like that. What we can do, we can split every block into equal number of sub-blocks, and every GPU will be responsible for that. How exactly to do this? So let's consider the construction of every block. As we might remember, it consists of few linear transformations. Let's consider one of these transformations, for example, V score. So we divide the matrix into 4 equal blocks, and every GPU is now responsible for its own block. And this is called tensor parallelism, and that's one of the most famous way of solving this problem. As far as I understand, almost all large models are trained in such a way. But there is an alternative way of doing this. We can do the following. We can assign the first GPU to only the first stage, then the second GPU to the second stage, and so on and so forth. So now every GPU will be responsible only for its own stage. We will split them in this way. But here's the problem. When you have a batch of data D, which comes to the first stage, all other GPUs are idle. So they have to wait until the first stage will provide the input that we can give to the next stage. The same with the second stage. You see that all other stages are idle. They don't do any useful work. We can better visualize this by the following picture. where on the y-axis you have all the GPUs, and on the x-axis you have the time axis. So you start with the very first batch. Okay. We have a time limit in this. So in 10 minutes the meeting will be over, and I will. So let's just, connect to the same meeting after that. I'm sorry for this. So yeah, basically when you start, you have the first batch that is on the first GPU. All other GPUs cannot do anything now. Then this batch is propagated to the next stage, and so on and so forth. So up until the point when we came to the latest stage, stage 4. Then we do the backward pass in the opposite direction and propagate it until we hit the very first stage. And the problem here is that the red area shows you all the time that we didn't have any useful work. So the utilization here is only 25%, which is bad. And the solution for this is a PipeDream, which is quite a popular method for solving this problem. There are different variations like gpipe and so on, but they are all basically the same. They have the same idea, is that after you process the first batch, you propagate it to the next stage, and now you have, so instead of just waiting for the first, the stage 1, instead of just waiting for the result from the batch 1, it starts superseding the following batch. And the same on the next time step, and the same on the next time step. And then we do backward pass, and after the initial stage where we still have some bubbles, you see that after this warm-up stage, we now have the stable stage where there is no bubbles at all, and we have 100% utilization. So this method is good, but here is the problem. Stainless of weights. What do I mean? Let's consider this batch that started on the step 9. It's started from the forward pass, and then it finished it on the backward pass on the same stage. What we can see is that in between these two time points, we have this red blocks where we have updates of weights, meaning that the version of weights that we had on the forward pass is not the same as we had on the backward pass. So basically, many updates had happened in between these 2 points. And this method still worked. So yeah, we can better visualize this problem here. And this is for every stage, we plotted the number of blocks updates in between forward and backward passes. You can see that, so initially it has some warm-up stage, but then it stabilizes, and we have this kind of delay for every stage, although it's bounded, but yeah, and it's also oscillating. But yeah, we have this problem that for stages between the forward and backward pass, we have some updates. And this method still converged, but people didn't know why until we found out. So we basically made a theory that allows to describe why PipeDream works. In order to do this, let's formalize the problem. We are trying to minimize f, where f consists of m mini batches. Every mini batch has its own loss function. And then for every stage, we define its own portion of weights. So we have s stages. Every stage has its own weights. And now on the iteration k, we denote the version of weights by wk. So every stage has its own sub-index k. And as I mentioned before, between the forward and backward pass, we have few updates of other stages. That's why we define the following vector, gk. It's the stainless vector that shows you the version of weights that was used for the forward pass for every stage. And now we define the following stuff. It's the stale model, which basically consists of different stages, it consists of different weights for different stages with different versions. Some kind of Frankenstein, but basically this encodes this idea that every stage now has its own portion of weights, and every weight has its own version. And let's do the following assumption, because this is kind of complicated to analyze. In PipeDream, everything is deterministic, of course, but you have this kind of weird dependence of the version between different stages. Let's do the following instead. Let's assume that this delay, the difference between the current iteration and the version that we had for any particular stage, is bounded by delta, where delta is this stainless bound. And this actually makes sense because we've seen on the previous slide that this delay is bounded. And here's the algorithm this is just a mathematical abstraction. This is not a real PipeDream algorithm. But now we try to simulate how PipeDream, not simulate, but make like a mathematical abstraction over PipeDream. So it's not determined, it's randomized version of the PipeDream. We have this step size, we have number of stages, initial point. Then we initialized all versions to be the same, to be 0. And for every optimization step, what we do, we select a delay vector randomly. In PipeDream, it's not random, basically. It's deterministic. We've seen the plot. But here, in this randomized version of this algorithm, which is easier to analyze, we select it randomly, and that's why, basically, this method is called randomized. Then we form this Frankenstein model, stale model, that consists of different versions from different stages of weights. And then we sample the stage index and mini-batch index randomly, which is a second reason why the algorithm is called randomized. Then we update the active stage that we selected randomly by using the stale model that we just formed, and we keep all other weights unchanged. And here's the results that we got for this abstract algorithm. If f is lower bounded and L smooth, and also for every stage you have the bounded block gradients, and we have this also. We also have this assumption for the bounded stainless. The convergence of this algorithm is the following. It consists of the number of iterations k. Delta 0 is the difference between initial and solution point. L is a smoothness constant, and G is block gradient bound. This can be split into 3 terms, where the first one is the regular optimization term, the next one is the stochastic term, and the last one is this stale term. And one can say that this is not the exact PipeDream, since we have this delta here, delta bound. But in the PipeDream, everything is deterministic. But also, in real PipeDream, we don't sample the mini-batch index and the stage index randomly, because everything is deterministic, and at every step we know what index and what stage should be performing. And the answer is yes, that's true, that's fair. But this is a more general method, because this is not about, this not only predicts how PipeDream should work, but also all PipeDream likes method. And basically, if you find delta for a particular PipeDream-like method, you get the convergence by using our theory. Now, I propose everyone to reconnect to the same meeting, because we have smaller and smaller time. I'm so sorry for that, because I didn't notice that I use my Google account, which is not connected to KAUST. So now I guess we'll just reconnect. Cool. Can you see my slides?
Yes.
Okay, thank you. Yeah, so basically now what we're gonna do is to find delta in order to understand how the convergence will behave for a real PipeDream. This can be done in the following way. So we consider the scheduling of PipeDream, which is deterministic, as I mentioned. And let's consider the point when everything is stable, so it's fully utilized already. And let's consider, for example, the batch 6. It's coming on the step 10, and then it's finishing on the step 17. And in order to understand delta, you basically have to understand how, like, delta shows you how many, what is the difference between the version on the forward pass and version on the backward pass. To do it, you just have to like calculate all of this, the number of these red blocks, which basically shows you how many updates was happening in between these 2 points. You can just, you know, by doing, by computing the square area of this rectangle and then dividing this by 2, you will get the answer. The height of this rectangle is s, because we have s stages. And the length is 2s minus 1. 2s because the batch has to travel in s time steps and then travel back in s steps also, but the size is 1 block smaller. So we substitute this and we get the following formula. And if you look in our paper, you will have almost the same result, with except for this small addition term, O of 1, which stands for the fact that we could have even or uneven number of stages. So you have to be careful. But in case of even number of stages, the formula will be exactly this. And you can see that the delay delta is scaled as a square number of stages. So more stages you have, the more delay that will produce. Now we can finally use this delta in order to predict what will happen with the real PipeDream, not randomized version. So we substitute this delta in our convergence theory. We also substitute the tuned step size in order to reduce the number of parameters from the convergence rate. And here's the rate that we got. You can see it's scaled as the s in the power of 4. So more machines doesn't necessarily mean that you will have better convergence. And that might be one of the reasons why PipeDream is not as widely used as tensor parallelism, or it's used with a smaller number of stages. And here's the comparison of randomized PipeDream and PipeDream. So we actually, like, before we have to ask them ourselves, like, can our theory describe the real PipeDream well? And you can see that the blue line here is the real PipeDream for a simple quadratic objective. And this, all other lines are randomized version of the PipeDream with different delta bounds. And if we set the delta to be exactly the same as our theory provided, we can see that the red and blue line are behaving in a similar way. So that's the price of removing all these bubbles. You remove bubbles, but you have this problem with the fact that you have stainless term and you have different version of weights. And the next question that we asked is, can we somehow avoid idle time, but also avoid delay, avoid this tail term? That's the next contribution of our paper. We suggested to use a local SGD algorithm here, and it works in the following way. So in the beginning, we have this naive scheduling, where only one trajectory is, like, only one kind of trajectory is traveling in this pipeline, and almost everything is idle. But then what you can do is you can independently run a second trajectory. And then after one local step, you synchronize these two trajectories. Here is the point where you synchronize. You just have to average weights between these two trajectories. You can do the same, and you can see that you have reduced in the idle time. You can do the same, you can increase the number of trajectories by 1. And finally, you can do with 4 trajectories, and the stainless, the idle time will be the smallest. You still have bubbles though. So because after every one local step in this scheduling, you have to synchronize, but you can Instead, what you can do, you can use 2 local steps. And here is the result for 2 local steps of local SGD. You synchronize after 2 local steps, and you have a portion of time where everything was utilized fully. And you can even... Okay, that was someone talking. So yeah, and finally we have the result for when we have 3 local steps of local SGD. We see that the utilization is even higher. The only problem here is that when you do more local steps of local SGD, you have more diverged trajectories, because once in a while you have to average them. So you have almost the same kind of problem, but you solve it in a different way. Yeah, here S is the index of stage. You have R trajectories, which we found out to be the best when it's equal to the number of stages. And then here is the convergence for this local SGD. It's good because we don't have to reinvent it. We just have to adapt it for our case. And yeah, it consists of few terms like number of iterations, number of local SGD steps. Yeah, and sigma is the variance of the gradient. In the same way, it can be split into 3 terms. The first one is the regular optimization term. Then we have a stochastic term because of the fact that every gradient is not exact. And we have finally this tail term that happens because you have to synchronize, like you have these local steps, the number of local steps, and when you increase it, these trajectories diverge. And here is the rate that we got for local SGD. You see that it's s cubed h squared. If you compare with what we had for PipeDream, we see that in PipeDream we have s to the power of 4, whereas here we have s to the power of 3. But also because of the fact that we have this local updates and we have to average models once in a while, we also have divergence. So we multiply by the number of local steps. So it's not obvious what method is the best in what case. For example, here's the example when local SGD is better for some logistic regression. But here's the problem where PipeDream is better. So it doesn't necessarily follow that one of the methods is better than the other. It depends on the experiment, but yeah, anyways, before you train, you actually have to make a small experiments with different kind of scheduling. That's it for today. If you have any questions, I will be happy to answer. Let me just do it that way, that you can see the full picture.
Great, so this was an amazing presentation.